Welcome to Unit 4 in the first module of the course. This is an important unit because up until now we've treated the virtual machine as an abstraction, and from now on we are going to actually build it. So to begin with, let's take another look at the VM abstraction. And basically I'm repeating the quiz that I gave you in the last unit. And in this quiz we started with some arbitrary stack machine state, and the question was which VM commands will implement the abstract operation static2 equals argument 1, leading to this final stack machine state. So you saw the answer, and the point that I'd like to make now is that everything that you see here is completely imaginary. It does not exist for real. And if we want to actually execute this scenario in some concrete way, we have to realize it on some von Neumann machine. So what do we have to do? Let's think about it. If you had to do it, how would you go about it? Well, first of all, you have to take these 4 memory segments, or actually we have 8 of them, and we have to somehow map these memory segments on the single RAM that is available for us. And to do it in some sensible way, right? We have to remember where each segment starts on the RAM and manage these locations and so on. And once we come up with this mapping, we have to do something with the commands, with the push and pop commands. We have to translate them into a sequence of machine-level instructions that will operate on this world that we just built on the RAM. So we have a lot of work ahead of us, but as usual, we'll do things one step at a time, and each step will be relatively simple and well-defined. All right, so in order to carry out the implementation of the abstraction, I'm going to use a technique known as pointer manipulation, which some of you may be aware of, and for some it may be new material. So I'd like to give you a crash course in pointer manipulation, and this crash course is going to last exactly 1 slide, so bear with me. Let us assume that we have a typical RAM, and we decided to use the symbols P and Q to refer symbolically to the first 2 RAM locations, RAM 0 and RAM 1. Now consider the following pseudo-assembly statement. D equals asterisk P. What do we do here? Well, here's the rule of the game. Asterisk P refers to the memory location that P points at. So the asterisk notation tells us that we want to treat P as a pointer. Now, if we didn't put the asterisk, if we just did D equals P, then presumably we'll get the value 257, because that's what P points at. P is equivalent to 0, so D equals P will give us the contents of RAM 0, and yet we said D asterisk P. So when we say D asterisk P, we imply an indirect addressing operation. So we look at the value of RAM 0, which happens to be 257, and we treat it as an address. Next, we look at the value of RAM at this address, which happens to be 23, and we store it into the D container. So D becomes 23. So this is the gist of indirect addressing. Now, if we have to implement this thing in, let's say, heck, then here are the 3 statements that will make it happen. We start with at P, and by doing this, it's essentially the same as at 0, because P and 0 are the same thing in our assumption here. And then we say A equals M. This will cause A to become the contents of the selected memory register, which is register number 0, and therefore A will now contain 257. Now remember that A is an address register. So once we put a certain value into A, like 257, automatically we're going to select register number 257 from the RAM. So this will become the selected register, which in the heck assembly language is represented by the letter M. And therefore, when we next say D equals M, we're going to get the value of this register, the currently selected register, number 257, and the value happens to be 23. Now, everything that we did here is quite similar to what we did in Project Zero of this course. And if you did Project Zero, you shouldn't be surprised by what I just described. If you didn't do Project Zero, then I strongly suggest that you stop the video, take about an hour or two of time and do Project Zero. Submit it, and only after you understand how to use the heck assembly language will you be able to follow the next modules and really do them effectively. So assuming that you've done that and you understand the heck assembly language, let's move on to the next example. You know, what is the meaning of P minus minus and then D equals asterisk P? Well, X minus minus is shorthand for X equals X minus 1, or sort of a decrement operation, and X plus plus is the same with increment operation. So if we do P minus minus, well, we now treat P as a regular variable, and therefore RAM 0 will become 256. And now P points at address 256. So if we say D equals asterisk P, we'll get the value 19, which happens to be the contents of the RAM in 256. Here's another sort of final example, which is kind of symmetric. Here we do something that looks strange. We do asterisk Q equals 9. Well, asterisk Q stands for the memory location, which is addressed by Q. And Q happens to be 1024. So asterisk Q stands for RAM 1024. And we want to put in it the number 9. So instead of seeing 5, as we see here on the right-hand side, 1024 will contain the value 9. And if we then do Q++, RAM 1 will become 1025. Now you may ask yourself, you know, why am I showing you these two particular pairs of commands? Well, it so happens that these two pairs of commands will be used extensively in what follows. So I wish to once again emphasize that what we saw in this example so far is sort of high-level, or I call it pseudo-assembly code. And in order to actually implement it, you have to take every one of these instructions, pseudo-instructions, and rewrite them in your assembly language. If you use the heck computer, you have to write the code in the heck instruction set. If you use some other computer, you have to write the same code, which is seen here, using the target computer, the target language of your computer. All right, so moving along, here is how we implement the stack abstraction on a real computer. This is the abstraction. We saw it all along. And we see here an example, an arbitrary example in which we take a stack, we push 17, we get a different stack state. And what I want to show you next is how these two states are going to be mapped on physical memory. So here's the host RAM that we are going to use. And we're going to make two important assumptions. First of all, the stack pointer is going to be stored in RAM 0. And the second assumption is that the stack is going to begin in address 256, which looks like an arbitrary choice, but later on you will see that this choice actually makes sense. So with these two assumptions in mind, let us focus on the left-hand side of the slide. And the stack that we saw above, the abstract stack, which is 12 and 5, will be mapped on the RAM beginning in address 256, as we assumed. And therefore, the stack pointer, which always points to the next available location, now contains the number 258. Now, following the push constant 17, if we look at the top, we end up with the abstract stack state on the top right of the slide. And if we look at the bottom now, you will see that within the RAM, the number 17 ended up located in RAM 258, which happened to be the previously available space. And stack pointer has moved one position forward, so now SP contains 259. So that's how we're going to model it on the RAM. And of course, we now have to write the assembly commands that will actually make this transformation work for us. So the logic or the implementation of push constant 17 is going to be as follows. At SP equals 17, and the meaning of this is, go to the address that SP points at and put there the number 17, and then increment the address that SP points at so that the stack pointer will move one position forward, because we want it to always point to the next available location in the stack. So the next challenge that we have is to take these two commands and re-express them or translate them into assembly. And we're going to do it using the heck assembly language. So in heck, it's going to be as follows. First of all, we want to store the number 17 somewhere. And one way to do it is to say at 7, using the A register as a data register, and then D equals A. So we'll end up having the number 17 stored in the D register. Next, we want to do asterisk P or asterisk SP equals 17, and we do it as I showed you in the pointer manipulation demonstration. We do at SP, A equals M equals D. If you don't understand this logic, go back to the pointer manipulation crash course a few slides back and check it again. So this will accomplish the assignment of the value of D into the topmost stack location. And finally, we have to remember to increment the stack pointer. So for this, we do at SP, M equals M plus 1. Once again, I want to remind you that if you don't understand this code, you have to stop and convince yourself that you understand it. You have to practice it. You have to look back at the program that you wrote in Project 0 and make sure that you understand, this intricate business of indirect accessing, addressing using the A register. Note, if you look at this piece of code, we're using the A register here in two remarkably different ways. In the first two instructions, we use the A register as a data register. We put the number 17 into it, and then we move it into D. Now, the A register has this automatic side effect that it always selects a certain location in the RAM. So when we say, at 17, memory location 17 is going to be selected, but we don't care about it. We don't give it any attention, because all we want is to take the number 17 and move it into D. So who cares if it also selected something in the RAM? We don't care about it. In the next three commands, boy, do we care. In the next three commands, we use the A register as a classical addressing register. We set it up carefully using the pointer, and then we zero in on M, on the RAM location that the A register addresses, and we put the value of D exactly where we want it to be. So this piece of code is, has more to it than meets the eye, and once again, you have to make sure that you understand it before you continue with this module. Now, I would like to observe that there's nothing special about the number 17 in this particular example. And therefore, what we saw here is a general implementation of the generic command push constant I, where I can be any non-negative integer, right? All you have to do is replace 17 with I, and everything will work perfectly well. And that's actually what we do in the next slide. In the next slide, we look at the generic command push constant I, and we see that in order to re-express it in machine language, we have to use the two pseudo commands asterisk sp equals I followed by sp plus plus. Now, who is going to do this? The VM translator is going to do it. You have to write a program called VM translator, which you'll probably write using Java or Python. This program will receive as input a stream of VM commands, of which push constant I represent one of them. And given this input command, your VM translator is going to re-express it using several assembly commands that basically carry out the semantics which is described on the right-hand side. So on the right-hand side, we have the semantics asterisk sp equals I followed by sp plus plus, and you have to express this semantics in assembly. And once you know how to express it in assembly, you can write a program that actually does it in a very general sense, for any given push constant I command. All right, so the VM translator is a program that goes from the left to the right, that translates VM code into machine language, and each command like this one naturally is going to generate several assembly commands. All right, so this has been the module in which we began to talk about the VM implementation. So far we talked about implementing one command only, push constant I. And in the next units of this module, we'll talk about implementing all the other commands that we discussed before from an abstract perspective. Now we'll talk about how we actually make them work.